Hello everyone, my name is Rupinder Kaur and I am Science Mistress from Government Senior Secondary School Vapi. Here today we will discuss about the concepts of chapter whose name is Some Basic Concepts of Chemistry. So today the topic we are going to study about is principles followed for filling of orbitals in an atom, and the subtopics involved in this chapter are aufbau's principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity, and the electronic configuration of the atoms. So we will discuss these topics one by one. So our very first topic is aufbau's principle. Let us discuss what is aufbau's principle. And this principle states that the electrons are filled into atomic orbitals in the increasing order of orbital energy levels. According to the aufbau's principle, the available atomic orbitals with the lower energy levels are occupied before those with the higher energy levels. This means this principle is very basic for the filling of electrons in the orbitals, which state that firstly we have to fill the electrons in the lowest energy levels, orbitals with the lowest energy levels, and after that we have to fill the electrons in orbitals with higher energy levels. So here we will see how we have to fill the electrons in the different orbitals. So according to the different principal quantum numbers, we have different orbitals. That is, for n is equal to 1 we have 1s orbital, for n is equal to 2 we have 2 orbitals, 2s and 2p. For n is equal to 3 we have 3 orbitals, 3s, 3p and 3d. For n is equal to 4 we have 4s, 4p, 4d and 4f. For n is equal to 5 we have 5s, 5p, 5d and 5f orbitals. N is equal to 6, 6s, 6p and 6d. N is equal to 7 we have 7s and 7p. For n is equal to 8 we have 8s orbitals. So according to aufbau's principle, we have to fill the orbitals with the lowest energy levels. So they have given the command that we have to fill the orbitals first diagonally, that is the lowest one, and after that we will move to the further. The diagram clearly depicts, the arrow in the diagram shows that how we have to move to fill the orbitals. So firstly we will first fill 1s orbital, and after that we will fill 2s. After the arrow show that we have to fill 2p orbital, and after that then 3s, 3p, 4s and 3d. Here we do not have to fill the orbitals in the order, that is first we have to fill 3s, then 3p and 3d. No, this is not that type. We have to first move to the lowest one. After completely filling that, we have to proceed with the orbital with the higher energy levels. So here we will see the order, that is first we have to fill 3s, then 3p. After that first 4s will be filled and then 3d will be filled. Similar way, we will fill, after filling 3d we will fill 4p and 5s will be filled first, and after that 4d will be filled. So for filling the electrons in the orbitals we have to follow this pattern. Only after that we will be able to clearly put the electrons in the different orbitals. Hope you will understand, and we will see some examples how this principle works. Now let's come to the salient features of the aufbau's principle, and according to this, now let's come to the salient features of the aufbau principle, and according to this, the very first feature of this principle is that electrons first occupy those orbitals whose energy level is the lowest. This implies that the electrons enter the orbitals having the higher energy level only when the orbitals with lower energy level have been completely filled. This means that firstly we have to fill the orbitals with the lowest energy levels. When they are completely filled, only after that we will fill the orbitals with the higher energy levels. And the second feature states that the the order in which the energy of the orbitals increases can be determined with the help of n plus L rule, where n is principal quantum number and L is the azimuthal quantum number, and sum of these both numbers will determine the energy level of the orbitals. This means that first we should have knowledge about n and L. After adding n plus L, we will get the energy of the orbitals. And the very third feature states that lower n plus L value corresponds to the lower orbital energies. If two orbitals share equal n plus L values, then the orbitals with the lower n value is said to have lower energy associated with it. This means that we have to calculate first n plus L value. If we have two orbitals with the same energy level, then in that case we will consider the value of n. Lower the value of n, lower will be the energy associated to that orbital. Now the fourth feature of this principle is that the order in which the orbitals are filled with electrons is. So here they have given us the values according to which we have to fill the orbitals. That is, first we have to fill 1s, after that we have to fill 2s, then 2p, 3s, 3p. Firstly, you must properly note here that after filling of 3p there is no 3d. First we have to fill 4s orbital, and after that 3d will be filled, because the energy of 4s orbital is less as compared to 3d. Therefore we have to first fill the 4s orbital completely, and after that we have to fill 3d orbital. After filling 3d orbital, we have to fill 4p, then 5s, then 4d, then 5p, 6s. After that we have to fill 4f. After that we have to fill 5d, then 6p, 7s, 5f, 6d, 7p, and so on. So this is the order here given, which is for the filling of orbitals according to their energy levels. The lowest will be filled first, and after completely filling the lowest orbitals, we have to move to the next one having a higher energy. Now let's come to the exceptions for filling the orbitals, for filling of electrons in different orbitals. Here one of this exception is that the electronic configuration of chromium is 3d5 4s1, and it is not 3d4 and 4s2. This exception is attributed to the several factors such as increased stability provided by the half-filled subshells and the relatively low energy gap between the 3d and 4s subshells. Here the electronic configuration of chromium is 3d5 and 4s1. That is, one of electrons in the s orbital has been jumped to 3d orbital, so that its orbital will be 3d orbital will be half filled. As we know that half filled orbitals and fully filled orbitals are more stable as compared to the others. So this is mainly due to that reason that 4s orbital is has one of the electrons has been jumped from the 4s orbital to the 3d orbital in order to complete the d shell that is half filled. Moreover, there is very less gap between the 3d and 4s orbital, so it is easy for the electrons to jump from s orbital to d orbital by providing small amount of energy. So this is one of the exception. So our very next topic is Pauli's exclusion principle. Hope you all are clear with the last topic, that is aufbau's principle. Now let's come to the Pauli's exclusion principle. The Pauli's exclusion principle states that in an atom or molecule, no two electrons can have the same four electronic quantum numbers, as an orbital can contain a maximum of only two electrons. The two electrons must have opposing spins. This means that if one electron is assigned as a spin up plus 1 by 2 electron, then the other electron must be spin down minus 1 by 2 electron. So Pauli's exclusion principle basically depicts that we have to fill the electrons in an orbital with opposite spins. If one of the electron has positive 1 by 2 spin, then the other one should have a negative spin. If one has spin up, then other should have a spin down. So there is a picture in the slide which shows that a cross shows that because in 1s orbital the electrons are filled, one with spin up and one with spin down, but in 2s orbital both the electrons are shown with the spin up because they can't exist over there in the same orbital. So in the next slide they have given the green tick which shows that this configuration is alright, this configuration is okay. Why? Because both the electrons in the two different orbitals are filled properly, one with spin up and one with the spin down. As in 1s orbital the arrow is up and the other electron showing the electron arrow is down. In the same 2s, one with spin up and one with the spin down. So we must always consider in our mind while filling of electrons, then if we are filling two electrons in the same orbital, then one should be with spin up and other should be with spin down. Now after the Pauli's exclusion principle, let's come to the importance and application of Pauli's exclusion principle. So the very first point is that the Pauli's exclusion principle helps to explain a wide variety of physical phenomena such as the electron shell structure of the atoms and the way the atoms share electrons. So they in the very first point they have given the basic idea that this principle is majorly responsible for the physical phenomena like electron shell structure of atoms and how the electrons share how the atoms share electrons. And the very second point is it helps in describing the various chemical elements and how they participate in forming chemical bonds. So this principle plays a major role in depicting how the atoms participate in forming chemical bonds and how various chemical elements are formed and how they behave. So the next point is the periodic table can also be defined with the help of this principle. So we can also define the periodic table with the help of this principle. And the fourth point is this principle helps in describing the stability of large number of systems with many electrons and many nucleons. So this has played an important role in describing the stability of various systems and various systems involving large number of electrons and nucleons. So after completing our two topics, that is aufbau's principle and Pauli's exclusion principle, our very next topic is Hund's rule of maximum multiplicity. Now let us define what this rule says. So according to Hund's rule, before the double occupancy of any orbital, every orbital in the sublevel is singly occupied. That is, we have to first singly occupy each sublevel. For example, in 3p orbital we have three sublevels, that is 3px, 3py and 3pz. So we don't have to fill the very first level completely, we have to first singly fill each and every sub level. That is, first we have to fill 3px, after that 1 electron in 3px, 1 electron in 3py, and 1 electron in the 3pz. And the second point states that for the maximization of the total spin, all the electrons in a single occupancy orbitals have the same spin. That is, if we are filling the electrons one by one in each of the sub level, so we have to keep the spin of these electrons in these sub levels same. ठीक है? So this is the slide which gives us the clarity about how we have to fill the orbitals. For example, in the point A, we have first 1s orbital that is filled, one with spin up and one with spin down, 2s is completely filled, and in 2p they have shown that we have to first singly. This is the perfect example where we have shown that first we have to fill each of the sub level equally and with the same spin. So this is one of the best example to show the Hund's rule of maximum multiplicity. And in B, we have 1s fully filled, 2s fully filled, and in 2p they have first filled the one sub level completely. They have not given the preference that they first have to fill each sub level equally and with the same spin. So B configuration is wrong. In C, we have 1s completely filled, 2s completely filled, and in 2p they have singly filled each sub level, but in this they have not given the same spin to each and every sub level, each and every electron in the sub levels. So one is with spin down and other two are with the spin up, so this is the wrong configuration. And in D, we have 1s completely filled, 2s completely filled, and in 2p they have first sub level with both the spin downs, which is wrong according to Pauli's exclusion principle also, because in one sub level we can only fill electrons with the opposite spin. So this one is wrong. In the second one, they have shown both the electrons with spin up, that is also wrong. And in the third, that is spin with spin up. Alright, then in the configuration E, we have 1s and 2s completely filled, and after that they have first singly filled each and every subshell, and after that they are completing the remaining electrons with the spin down. So this configuration is also right one. So I hope you will understand the concept of Hund's rule of maximum multiplicity with the help of these examples, because these examples are clearly depicting how we have to fill the electrons according to the Hund's rule and different sub levels of the orbital. So here is this slide is for you, where you have to identify how we have used these principles and rules in the various examples. So firstly, you have to check out the configuration of all these elements whose atomic numbers are also given and configurations are also given. For example, the very first is hydrogen, whose atomic number is 1 and configuration is 1s2. And the second one is helium, whose atomic number is 2 and configuration is 1s2. They have shown the filling of electrons in the orbitals too. They have completely filled 1s2. They have not done that. They have first filled one electron in the 1s orbital and other electron in the 2s orbital. So this is showing, the second one is helium, is showing the example of Aufbau's principle, which states that first we have to fill the lowest energy level and after that we have to move to the higher ones. And the third example, which is of lithium, whose atomic number is 3 and electronic configuration is 1s2, 2s1. So they have also, this is also the example of Aufbau's principle, where first lowest energy 1s shell is completely filled, and after that they are filling 2s with 1 electron. Next one is beryllium, whose atomic number is 4 and the electronic configuration is 1s2 and 2s2. They have same filled in the similar manner. That is, first they have filled 1s orbital completely, and after that they have filled 2s orbital. The very next example is boron, whose atomic number is 5 and electronic configuration is 1s2, 2s2 and 2p1. They have first filled electrons in the 1s orbital, then 2s and 1 electron in the 2p. And the next example is carbon, whose atomic number is 6, 1s2, 2s2 and 2p2. Here they have filled electrons in the 1s orbital and then 2 electrons in the 2s orbital with opposite spin, and after that they are filling single electron in the sub levels. That is, they are filling 1 electron in 2px and 1 electron in 2py. They are not filling the electrons completely in the 2px orbital. So here we have used the Hund's rule of maximum multiplicity. This is one of the example of Hund's rule. In the very next example, nitrogen, they are also following the same rule, whose atomic number is 7 and configuration is 1s2, 2s2 and 2p3. That is, they are singly filling the electrons in each of the sub levels of the 2p orbital. And after that we are given the example of oxygen, whose atomic number is 8 and configuration is 1s2, 2s2 and 2p4. Here you have to check out clearly that they are first filling 1s orbital completely, 2s orbital completely, and after singly filling each and every sub level of the orbit 2p orbital, they are filling the double electrons. That is, they are providing the multiplicity to the electrons in the same orbital but with the opposite spin. So you can also you could also be clear from that. First they are using the Hund's rule for filling singly filled the electrons, and after that they are using the Pauli's exclusion principle. That is, in the single orbital they are putting electrons with the opposite spin. So similar examples are also given for fluorine, whose atomic number is 9 and electronic configuration is 1s2, 2s2 and 2p5. 1s is completely filled with electrons of opposite spin, and 2 is then filled. After that 2p. In 2p we have 1s. They have first singly filled each electron with the same spin, and after that they are putting the remaining electron with the opposite spin. After that we have neon, whose atomic number is 10 and configuration is 1s2, 2s2 and 2p6. That is completely filling of orbitals. 1s is completely filled, 2s is completely filled and 2p is also completely filled. So you can use all these three principles to fill the electrons carefully, and this is one of the best way for finding out the electronic configuration, orbital configuration of the different atoms. So in this slide, electronic configuration of different atoms are given. For example, for hydrogen, atomic number 1, it is 1s1. For helium, it is 1s2. For lithium, it is 1s2, 2s1. Beryllium, it's 1s2, 2s2. Similar for different atoms, for boron, carbon, nitrogen, oxygen, fluorine and neon. For neon, atomic number is 10. That is 1s2, 2s2 and 2p6. Here the electronic configuration is fully filled. And after that we have sodium, chlorine. Some different elements are given. Chlorine is given, potassium is given, alright, iron is given, scandium is given. So different configurations are shown in this slide, and one should note that all the numbers in the electronic configuration add up to the atomic number. For the element example, it's given for neon Z is equal to 10. That is the electrons that we show in different orbitals add on to give the atomic number. That is, electrons in the neon are 2 plus 2 plus 6, that is 10. 10 is the atomic number of neon. So hope you all get this. So here in this slide we have, there are several notable exceptions to the order of electron filling for some of the transition metals. Chromium, whose atomic number is 24, and copper, whose atomic number is 29. Its electronic configuration is 4s1 3d5 rather than 4s2 and 3d1. Similar for copper, its electronic configuration is 4s1 and 4s1 3d10 rather than 4s2 3d9. The reason for these anomalies is the slightly greater stability of these subshells that are either half-filled or completely filled. That is, the exceptional behavior shown by these atoms is because half-filled d orbitals or fully filled d orbitals are more stable as compared to the other configurations. That's why one of the electron from the s orbital jumps to the d orbital so as to complete their electronic configuration half-filled or fully filled. So basic reason is the stability. So half-filled and fully filled d orbitals are more stable as compared to the other ones. In the last slide, we were given the configuration of chromium. Now we are being up to with the configuration of the copper, whose atomic number is 29. It is clearly shown in the slide that one of the electrons from the s orbital has been jumped to the 3d orbital, where all the 5 sublevels in 3d orbitals are fully filled. So this is mainly due to the relative high stability of the d orbitals as compared to the s orbitals. So that's why d configuration, whether it is half filled or fully filled, more stable. So that's why one of the electrons jumps from s orbital to the d orbital, showing some anomalies in the electronic configuration of copper and chromium. So this slide is for shorthand notation practice. That is, when you are at higher atomic number, you can use the last noble gas core, and after that you have to return the higher energy electrons. You are given some examples. For example, aluminium, calcium, nickel, iodine, astatine. So you have to write down the electronic configuration, but with the last noble gas electron core. So in the previous slide we were given the examples for practice. Now we will see the electronic configuration of the different elements. So the first one is aluminium. Its electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p1. In spite of writing the complete configuration, we are using the last noble gas core. That is, neon has atomic number 10, so we are using neon. After that we are using the higher electronic configuration, that is neon, and along with 3s2 and 3p1. For calcium, we have electronic configuration 1s2, 2s2, 2p6, 3s2 and 3p6. It is the electronic configuration of argon. So we are using argon in spite of writing down the complete configuration and along with the higher electrons. Argon along with 4s2. In case of nickel, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. So in spite of writing down the complete structure, electronic configuration, we will write down argon along with the higher electrons, that is 4s2 and 3d8. Similarly, in case of iodine, we have electronic configuration of the previous noble gas core, that is krypton, and along with the higher electrons, that is 5s2, 4d10 and 5p5. Alright, then in case of S10, we will write, in spite of writing down the complete electronic configuration, we will write xenon along with the higher electrons, that is 6s2, 4f14, 5d10 and 6p5. Alright, so here are some of the electrons. Hope you all are clear with the concepts of different principles, and thank you for listening to me carefully.